This video is a series of 5 videos in which we will compute the performance of a 24-slot, 8-pole spoke motor using the transient magnetic solver of SOLIDWORKS 2D. In this part, we will first start by defining the rotor angle, which is the angle between the top planes of the rotor sub-assembly and the motor assembly. Its value is set as 0 degree, and to permit a rotation in the anti-clockwise direction, which is the positive one, we should click on flip dimension. By clicking on the defined rotor angle in the mates, we can double-click on the 0 degree value to define it as a global variable, then name it as rotor angle. For a better integrity in SOLIDWORKS 2D motion, we should properly define the rotor angle by clicking on Manage Equations. Then, add the degree to the null value of the defined global variable. Defining the rotation direction is very important in motor applications, and to better understand the rotation behavior in SOLIDWORKS, let us edit the rotor angle from the Mates section. First, we can change the null value of the angle to 15 degrees, for example, and see that the rotation direction will be anti-clockwise since the flip dimension option is checked. The alignment option of SOLIDWORKS enables the alignment of vectors normal to the selected planes in the same direction. Now, by unchecking the flip dimension, the rotation direction is switched to the negative one, which is the clockwise direction. Now, let us redefine the rotor angle value as 0 degree and click on OK. To well define the motion inside SOLIDWORKS 2D, it's important to add a band which envelops all the rotatory parts. The band should preferably be in the middle of the air gap between both the rotor and stator parts. We first add a new part and name it as band. Then, we create a sketch on the front plane and draw a circle of diameter equal to 39.5 mm, which is calculated using the shown formula. Then, we create a surface using the planar surface option. Once done, we can rebuild and save the model. Band part is stationary, and thus we can make its origin fixed to the motor assembly origin using the coincident mate. In the same way, we can also fix the stator origin to the global one. The rotor is the rotatory part of the model, and therefore we should define its mates cautiously. First, we can create a coincident mate between its front plane and the global one. Now, the rotor should have the same axis of rotation as the motor assembly. To define the global axis of rotation, we select both the global top and right planes and click on Axis from the Reference Geometry section, then select OK. To define the rotor rotatory axis, we proceed in the same way, only this time selecting both the top and right planes of the rotor subassembly. Now, we can define both the created axis as coincident. Color the south magnets. We right-click on the part and then select Appearance of the magnet part. We can choose the blue color for the south magnets. The north magnets can be colored in red in the same way. To define the PM's magnetization, it's important to define the local coordinate systems of the magnets, giving their rectangular shape. To do so, we click on Reference Geometry in the Assembly tab and select Coordinate System. For the magnets which are diametral opposite, the definition of one coordinate system is sufficient. For each coordinate system, it's crucial to define the origin point, which is the side point of one magnet, and the x and y axis corresponding to perpendicular sides of the rectangular magnet. Now, as we have reached the end of this part, well done, and see you in the next part.